Guys, this is going to be a lecture on graph neural networks. So before we get started on graph neural networks, it's important to understand what graphs are. Um, Graphs are basically a collection of nodes and edges, and these nodes and edges can represent a whole range of different information. They can be about roads on a highway system. They can be about social networks, where each node is like a person. They can be used to model protein interactions in the brain or in the human body, where each node would be a protein and then each edge would be some sort of interaction between each protein. And so graphs can be applied or can be used to represent a whole range of different systems in the world. And so it would be useful if we had some sort of deep learning approach that could understand and analyze these networks, these graphs. And that's what graph neural networks are all about. So before, just to understand what we're trying to go for here, uh, the goal is to actually generate some sort of embeddings for each node in a graph, right? So, uh, and then once we have some sort of vector representation for this node and this node and this node and all the other nodes in the graph, we can then use these embeddings to do something interesting with them. And I'll talk exactly about what we can do on later slides, but the goal for these sort of graph neural network tasks is to generate these embeddings um, for these nodes. And this is just some sort of vector representation that contains information about data in the node itself, as well as information about the neighboring nodes. And so hopefully that makes sense. So if we want to somehow we want to generate these low dimensional embeddings for each node in our graph, how can we do that? And can we do that with traditional deep learning approaches? And that's probably the first question to ask. Can we use the tools that we've already learned? And so imagine if this is something called an adjacency matrix, where just this part of this matrix, where each row and each column represent a node, and so you can see basically there's a 1 everywhere there's a connection, right? So there's a connection between A and B, or there's an edge between A and B, and so there's going to be a 1 A and B, and there's going to be a 1 with B and A, because this is an undirected graph. So using an adjacency matrix like this, you could imagine that we take in this, let's say we wanted to calculate the embedding for node B. We would take in this row of this matrix here, which represents all of the neighbors of B, and then we also include some features of that node. Maybe this is representing like a social network, and so these features would be like the age and then the gender. I know that doesn't really make sense for 0, but let's say that that's what it represents, and then we take this entire vector, put it into a neural network, and then output some sort of embedding that we can then use for some other task. We basically were able to encode the information about this person's age and gender, as well as the information about all the surrounding people's age and gender, by creating this low-dimensional embedding. Now that seems like it would work, right? The only problem is, okay, first of all, adjacency matrices are very sparse, and it's all 1 or 0, right? So as you get larger and larger graphs, this is a really small graph. Imagine if you had a graph that was sort of representative of a population on a social network. That would be huge. And so this would be a very inefficient way of representing all that data. Furthermore, these are size invariant representations, right? If you imagine we added another node to this graph, then our input vector to this neural network would be one dimension larger. And then since the inputs have to be size invariant for neural networks, because you have a fixed number of layers in the first layer, you won't be able to use the same neural network if you have another node. Another issue is that if you sort of flip these, obviously these are alphabetically ordered, but a lot of times there's no inherent way to order the nodes in a graph. And so if you flipped around this order, this feature vector would be entirely different. And for neural networks, the order in which you present the information matters because it learns the connections in the order that you present it during the training data. So if you change it up later, it's not going to work. And so for those reasons, we can't use traditional, like a multi-layered perceptron or even like a CNN to sort of gain insights and create these embeddings for each node in a graph. And so we need some other approach. So the key idea behind graph neural networks is to generate an embedding, as I mentioned before, for each node in the graph. And then after we generate this vector, right? So this is like an input vector that um, that we have about this data. And after doing some stuff with this input vector, as well as the input vectors of all the other nodes in this graph, we want to output some embedding for node V that represents all of this information as well as all of the input information for all the surrounding nodes. So this embedding should capture all of this information, and that's what we want to create. Now, once we have this embedding, there's a lot of things that we can do with it. One thing you can do is node similarity calculation, which is once you have this vector representation of this node, you can compare it to vector representations of other nodes and then see which two nodes in the graph are similar. Another thing you can do is node classification. So let's say this was a social network graph, and you were trying to figure out, given some characteristics of this account, maybe each node represents an account, you can figure out who is a human or a bot, right? And then, so once you have these embeddings that you create for each node, you can then pass it on to some other neural network or some other classifier that inputs this vector and then tells you if it's a bot or a human. And so you can do node classification. Another thing you can do, which we won't really cover, there's a typo here, this time, is graph classification, not classification, where you take the embeddings of all the nodes in your graph, and you somehow combine them and then are able to extract some meaningful information about the whole graph itself. And so there's a lot of things you can do with these embeddings, but the important thing is actually creating them in the first place and making sure they actually represent the neighborhood information as well as the feature information of each node. And so that's what we're going to try to tackle. So a key idea to observe that's really behind how graph neural networks work is the idea of a computation graph, right? If you think about the neighbors of each node, the neighbors all form a sort of computation graph, and these graphs are ordered according to the distance from the root node, right? So if you take the yellow node here, in the first layer of this computation graph, you have blue, green, and red, and these are all the nodes that are one edge away from this yellow node, right? And then from all of those nodes, you have all the nodes that are one distance away from that, right? So for example, for this blue node, the only node that's close to it with one distance away is A. So you put this yellow node here. For the green node, there's 4 nodes that are one edge away from it. The red, I guess that's yellow, purple, and pink. And then you have all of those here. And the same thing for red. Now these graphs have a depth of 2. You go at most 2 edges away from the root node here, but you can imagine we could keep extending these graphs for a while. And so the key here is that at every gray box that you see in these computation graphs, we somehow aggregate all the information. If we're creating these embeddings, then we take the embeddings for these two or for the nodes in this layer, aggregate them somehow, and then give it to this node. And then we somehow take the embeddings for this node and this node and this node and aggregate them together, and then somehow that represents the embedding of this node. And so by doing this sort of aggregation step, we're able to represent in each embedding all of the neighborhood information, uh, all the information that's in the neighborhood of this node, right? And that's essentially what we want to do. We want the embedding of each graph, of each node in the graph, to represent the graph's own information as well as all the neighborhood information. And so this idea of a computation graph is key to understanding like how we do this. And so now we're going to be talking about basic neighborhood aggregation, which is the exact mechanism that we perform on the computation graphs in order to get the final embeddings. So as we saw before, this is like the computation graph. It's oriented just sideways. And essentially at each gray box, we want to do aggregating of all the embeddings of the previous layer's nodes and then somehow combine it with information of this node itself so that our embeddings are they reflect both the neighborhood information as well as the node's current information, and we pass that along the graph. And at the end, we have the yellow node's final embedding, which captures all the information from all these nodes combined, all these nodes combined, and then you have like a really good representation of the neighborhood data and this variable's own data. So we somehow want to create that. And so this is how we can create it. So we start off each node's embedding by just setting it to the feature vector that we had before, right? So if this was like a social network analysis, the feature vector would just be the age, gender, like it would contain all the information about a specific account, right? Each node has this. And then at layer k of this computation graph, where this would be like where the bottommost layer would be layer 0, this would be layer 1, and this would be layer 2. This is what we do on step k. So at each step, at each like k value, we have a weight matrix, two weight matrices. And so wk is the first weight matrix, and we multiply this weight matrix with the sum, the normalized sum. This just means normalizing across all the neighbors. The normalized sum of all the embeddings of the previous layer's nodes, right? So for example, let's take this component here. What we would do is take the current embeddings, or the layer 0 embeddings for A, B, E, and F, add them all together, all normalized, however. We have to remember this term. And once we have this sum, we just multiply it with this matrix WK, or this vector WK. And then this here, this is BK is a second weight matrix. It's not a bias, I thought it was a bias when I first saw this, but it's another weight matrix. And then what this means is this is actually the current node's own embedding in the previous layer. So that's kind of hard to understand here, so I'm going to go back a slide. If you imagine, let's say we're trying to find, let's say we're doing it for green, right? And we want to find the previous layer's embedding. What we would do is take the embedding here, right? This is sort of from layer 0, although it's like in a different computation graph, it would be the exact same sort of data. And when you're implementing this, you actually, to like be more efficient, you would actually like save all of this as you go and be able to look it up easily. But for example, like the previous layer's embedding would, if you're trying to calculate it for this layer here in this computation graph, would be what's contained here, for example, or here, or here. Anytime there's a green node in the bottommost layer. And so the reason why you include this term is because you not only want to have all the neighborhood information, which is basically stored in this place here, but you also want to somehow combine the old embedding of the current node to hold in the information that you got from this place. And so that's why we do this. And then once you multiply, once you get the products and then find the sum of those two products between these two weight matrices and the respective components, you have some uh, you have some data, or you have some value, and then you pass that through some nonlinearity function, um, and this is just like sigmoid, ReLU, or tanh. And then you have your new embedding, and this is going to be some vector. And then you repeat this process, right? So if we do this for all of these nodes here, for B, C, and D, and then now we repeat the same process for A, and then um, we get the final embeddings here. And so if you think about it, each gray box here, where we're doing this step of multiplying the sum and then the previous embedding with these two weight matrices, it's basically a neural network. Even though we don't have a bias term here, and we have sort of like two inputs, I guess you can we're just applying some weights and then doing a nonlinearity, and that's what a neuron in a neural network does. So you can almost think that this is this each of these boxes is like one layer of a neural network, where you input the average sum of all of these embeddings in combination with this node's previous embeddings, and then you somehow generate a new embedding, and then you pass that onwards. And so it's like sort of like a meta neural network, kind of like you have neural networks in all of these gray boxes, and it's not really a network, it's like a single layer of a network. But hopefully that made sense. And so how do we actually train the weights? We had all these weights in these gray boxes here, two for each box, but how do we train those parameters? So there's several ways to do this. You can either do it like with unsupervised techniques. So basically, this you want to incentivize the embeddings of closer nodes to be more similar, and there's many ways you can sort of capture that information. I've listed a few on this slide, but basically, you want embeddings of nodes that are close together and similar to be similar, right? That's kind of obvious. So you would I'm not going to go like the into depth here on how to do the unsupervised ones, but you can look them up if you'd like. If you're trying to do a task like node classification, however, where each node has some sort of characteristic attributed to it, like if this is a social network analysis, then you could say, is this node a human or a bot, right? And then you somehow want your embeddings to capture the information of whether or not it's a human or a bot. And so what you can do is, the output of this node is going to be an embedding. It's going to be some sort of vector. And so you also have to define some parameter, some sort of vector that is able to transform the embedding vector into a sort of discrete category, all right? But once you do that, you can define sort of just a cross entropy loss function. This is just like your standard categorization loss that you do in traditional deep learning, like for uh, like a like MNIST or something, and then you can just train all the parameters, including the newly defined classification weights that turn each embedding into a discrete sort of output. And you can train all of that by just doing gradient descent on this loss function and making sure that out of all the nodes that you're training on, you get more. You try to make as many of them right as possible, right? So you sort of optimize for this loss function. And this is sort of a very simple loss function. You can like do very complex like hand designed loss functions that really capture what you're trying to do in your task. And yeah, there's also mixed loss functions where you take some of the unsupervised stuff, where you do like node similarity, and also have some of your own objectives built in. So when you're training these graph neural networks, what you do is in your graph, if you have several nodes that you know the values for, you basically take those nodes and then you generate the computation graphs for all of those nodes, and then you train using backpropagation, for all of these nodes. And this is basically like your batch, or like your Yeah. And so if you do that, then the interesting thing is that you have some inductive capabilities that emerge, right? If you are paying attention, then you may be wondering, like, you may have thought, oh, maybe these weights are all like different for each computation graph, but actually they're all the same, right? So you can actually use the same weights for any node in your graph, and like, you don't have to retrain for different components of your graph. And so if you ever have a new node that gets added to your graph, then uh, you don't have to retrain anything. You can just, if you want to generate the embeddings for that node, you can actually just use the same weights that you learned during training, and then just output the embedding on the fly, on demand. And you can even use the same weights for a completely different graph if the graph has some sort of similar structure, or it's representing sort of the same type of information. And so this is probably the most interesting part of graph neural networks. It's like the generality of the weights that you're training. And so now I want to briefly talk about sort of newer variant of graph neural networks. There's like a whole bunch, but this is sort of to get you acquainted with the idea that the aggregation technique that we used can be anything really. And graph convolutional networks are this specific formalization of it was introduced in a paper in 2017, and basically since that time, or like around that time, there have been a lot of papers that propose different aggregation techniques using a whole bunch of methods. And so as long as the aggregation technique is differentiable and you can conduct backpropagation with it, then you can pretty much do anything you want to combine the neighborhood embeddings and the old current node embeddings. Um, you can do anything you want, right? And so there have been a whole host of different ways to do that. I'm going to talk about one here, the which is a GCN neighborhood aggregation. And basically, this is almost the same thing as the basic technique that we talked about earlier, except um, we use the same weight, WK, for all of the neighborhood nodes as well as our own node's previous embedding, right? So we don't have this sort of BK secondary weight that we use to multiply with our old node's embeddings. Instead, we just have one weight, and we do the union of all of our neighborhood nodes as well as the current node. So we don't have two weights here. Um, and we also do a slightly different normalization technique. And basically, the advantage that this has is that it it doesn't it lessens the effect of um, high magnitude embeddings of neighborhood of the neighbors. So that's not super important, but basically this whole idea, which is kind of the coolest part, I think, is that you only need one weight instead of the two. It actually works better than the basic neighborhood aggregation, and like significantly better. And so this is just one variant of a graph neural network, and there's a whole bunch where the exact stuff that goes on here is different, and it uses many other techniques. So as I said, as long as this part is differentiable, you can do whatever you want for the aggregation. And so there's lots of cool applications of graph neural networks. Um, as I mentioned before, there's like graphs can be used to represent a whole host of different systems. Here I've listed a couple of animations from uh, a couple projects that have used graph neural networks. This project used uh, graph neural networks to basically model glass particles that are in glass, and so by using graph neural networks, they were able to understand and predict, like accurately predict, the mobility of particles in glass. it turns out that like particles in glass aren't like completely solid, or like they're not completely fixed, as in any solid, but like graphs are surprisingly fluid. And so this by using graph neural networks, this project, the team that did this project was able to outperform the previous state of the art in modeling glass particle mobility. And this project here is Google actually like use graph neural networks to improve the ETA estimates on Google Maps. They use like a pretty like complicated variant of a graph neural network, I think, or it's much more complicated at least than the one that is described in this lecture. They also incorporated like edge information, I think, not just like the node information. I'm not completely sure, um, but this is just to show like the wide ranging applications that graph neural networks can have. And also, interestingly, I've also read that people have been using graph neural networks to like approximate solutions to sort of the traditional CS problems, like traveling salesman problem, or any sort of other graph optimization problems. Um, Again, I'm not like very familiar with those, but if you are interested, then make sure to check them out. And if you want to get started implementing graph neural networks, these are some libraries and frameworks that make it a little easier. Granted, there is like a kind of high barrier of entry, or there's like a high learning curve to getting started with these libraries, so it might be a bit difficult. Um, but yeah, these are some very well built libraries that can do stuff for you. And just to say, all the images that I haven't cited in this video are from this PDF, from this slide that I found online. All right, thank you.